Now let's go through some. Okay. Now this is, you saw this, right? Why does it look like that? This is the probability of different number of heads. Okay. I put 0.5 to make it a fair coin, right? Heads or tail. 7 means 7 times. Okay, you can see that binomial distribution 7, 0.5 means n equal to 7. The number of independent Bernoulli trial, independent identically distributed, with probability p equal to 0.5. If you did this, if you toss the coin, how many? If you toss, I was going to say if you toss the coin 1,000 times, but actually no. If you toss the coins 7,000 times, and each 7 times you record one number, you would have 1,000 records, right? Toss the coin 7,000 times. 7 times you add them together, another 7 add together, another 7 add together, you get 1,000 data points. You do the histogram, it should look a little bit like that. Now this is what I mean by constructing. I knew that if n were equal to 7, p equal to 0.5, it should look exactly like that. That's probability. That's a model. That's a construction I created with my own hand. I know exactly what that number is. It is given by here, 0.0078125 and 0.625, blah, blah, blah. Okay? Right. Why do we get the bulk in the middle? Think of this. And this is where combinatorics, I'm not going to go over the detail very much because it's a little bit beyond the need, but if you think about it, how many ways can I get zeros? It's only one way. I toss the coin 7 times and I get tail 7 times. How many ways can I get 7? 1. How many ways can I get 6? 7 ways. Because I can say tail, head, 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 or head, tail, head, head, head. There's 7 ways. So if each of them individual are likely, remember the card principle? The basic events are the same, and you count the number. Basically, you only have one way of getting all 0, one way of getting all 7. You get 7 as many times, 7 as many times. So this is, you multiply this by 7, I think, if I'm right. 7 or 6. You should get this. Okay. Likewise, how many ways can you get 2? Well, a little bit more variation. You get the greatest variation when you're talking about having 3 or 4 heads, because you can have head, 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 or various combinations. And that's the combination. Analysis of combination in mathematics called combinatorics. And this is how you build up probability model. Okay. Now you don't have to build anything, because mathematicians for the past, 200 years, not the past 200 years, the 200 years before the last 200 years, long time ago, 15th century, dark ages, when you have knights and whatnot, those were a little bit after that. Okay. So in the dark ages where you still have plagues, mathematicians were already doing the homework for you. So all this formula already done. Okay. So let's look at a cumulative version of that looks a little bit like this. All right. So I plot. Now I call this CDF. This here a little sort of like window dressing, make it look nice. If I didn't have all this, it would just look like sticks. That's it. Now, this is another one. Okay, this is called exponential distribution. I've plotted both the PDF and the CDF on the same graph. The orange or the yellow, obviously that's the CDF, right? Because it maximizes at 1. If you take the derivative of the blue, you get the yellow. Oh, sorry. If you integrate the blue, you get the yellow. If you differentiate the yellow, you get the blue, right? That's that. Simple as that. Okay. Now, let's look at common distribution. The first is again the Bernoulli. Oh. Yeah, by the way. See? Actually, it's if you have one coin toss, well, we'll talk about it later. As a homework, maybe I should have you guys look at this as homework. Look up Pascal triangle. Okay? It enters into binomial distribution, but that's not so important. Well, it is important. And next week will be more important because it will be in differential calculus. Okay? This is called, so you see that? This function is called binomial. And this function is the binomial PDF. So if I write down the formula to compute that stack that you saw earlier, the formula is 1 minus p to the power n minus x, p to the power x multiplied by this binomial term. Now, what does this mean? The probability of getting x number of heads. Well, what's the probability of getting a head? It's p. And you want to get how many of them? X. So the p of the x. Right? Can you see that? Let me make it a little bigger. Right? And what about tail? What's the probability of a tail? 1 minus p. How many of them do you get? Well, if you toss the coin n times and you get heads x times, how many tails do you have? N minus x. And because they are independently distributed, what's the joint probability? You multiply them. So 1 minus p times 1 minus p times 1 minus p, n minus x times. You get that. But that only gets you one configuration. For example, if x is equal to 3, this will give you the probability of head, 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 tail, 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 tail. But then you are ignoring the probability of tail, 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 head, 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 or head, tail, head, tail, head, tail, tail, or head, tail, tail, head, head, tail, tail. Okay? And how many combinations are there? That's given by the binomial term. Okay? Binomial term. So basically, you go down here, you look up something like this is going down for n, this is p. So n equal to 0, 1, 2, 3, 4, 5. N is equal to 5. And you choose 1, 2, 3. There are 10 ways. So how many ways is 10 divided by, 1 plus 5 plus 10 plus 10 plus 10. So those are the odds. You can see that this builds up. So as I increase the n, for example, earlier I put down n equal to 7, right? So let's say I put n equal to 5. I get a different one. In fact, you get this. You get this same combination, this ratio here that you saw. Okay. Now, if I want to go to higher, let's say I want to 6. Oops. Okay. Then you're going to have 1, 5. This is the number of combination. So you're going to have this profile. So let's create that profile here. See that profile? 7 numbers. One, two, three, 4, 5, 6, 7. Okay, so that's basically that's what was done, you know, in the 15th century or something. Okay. Now, so this is even, once again, I can do this, right? And I can put it inside manipulate, so I can play around with it. And basically this, I can do all kind of stuff, right? I can move the P around, I can move the N around. Yeah, I can look at the cumulative version, and I can increase the N, increase the P, all kind of stuff. And I can do this and just write a little explanation and then put it up as mathematical demonstrator. Okay, so maybe another homework, instead of you going to the mathematical demonstrator, you should build one. That'd be nice. Okay, that'd be simple. No, basically what you do is all the parameters you have, right, just make it selectable, that's all. Okay, so you can imagine that technique, it's like you see the histogram in real life, and you decide that you're going to use this, and then you just fiddle around until this thing matches the histogram. Okay, but in reality you have more clever way of doing it. Okay, now, so let me quickly go through, in fact, the list are given here. These are the key ones. Exponential, yeah. But I would refer to gamma, chi-square. These are all important. I think what I might do is, well, let's see what happens. Let's go to Wikipedia page. I think let's see if we can use the internet resource for our benefit. Wikipedia, the normal distribution. Obviously, that's going to give you a normal distribution. The point is, when you go to the bottom, very bottom, there'll be a little menu. Okay, this is all thing about normal distribution. It's very long because it's very important. Okay. But if you go to the bottom, there'll be a little menu section called probability distribution list. Right? That's it. This is what I mean by the bags of tricks that you take to the work site. Okay? Are you dealing with univariate? Are you dealing with discrete? Continuous? Okay? So let's say those are the ones that are familiar to statisticians. But I'm only asking you to look at this one, Bernoulli. Poisson. Not binomial, Poisson. Uniform. Negative binomial maybe. Okay, for continuous, I'm going to be asking you to look at gamma, maybe gamma. Beta, with beta, where are you? Beta. Where are you with bounded interval beta? Okay, right? Chi-square. Now, I want to teach you how to look at this table. How is it organized? You notice it's a probability distribution list. Left hand side, discrete with finite support. Discrete with finite support. Finite support is a mathematician's way of saying can happen. The set of values that can happen is finite. So if I toss the coin 7 times, what is the support set? It is 0, 1, 2, 3, 4, 5, 6, 7. It's finite, so that's finite. So if I'm talking about binomial distribution, I'm going to look for discrete, finite. There it is, binomial. Okay. Now, if I look for discrete but infinite, meaning it could be number of events that's infinite. There's no upper bound. Now, for example, forest fire is very rare. But if you think about it, there's no upper limit, right? It could be 1,000, 10,000. So if I tell you that the number of forest fire looks like Poisson distribution, you're going to find it under discrete because it's discrete number, right? 0, 1, 2, 3, 4, 5, but infinite. So you'll find it here. See? Right? Now, with continuous, it's not countable, but it can be bounded. For example, between 0 and 1, it can be bounded to be positive. It can be unbounded. So if it's bounded, one side called semi-bounded. For example, stock return can be positive and negative, right? So it's unbounded. How about stock price? Well, stock price cannot be negative, right? It can go down to 0 and be worthless. So it's bounded, semi-bounded, right? Okay. How about something that is like a percentage? For example, the percentage of usability of something, that's between 0 and 100%. So it's between 0 and 1. I'm going to find it under continuous, unbounded. Sorry, bounded. For example, beta is like that. Okay. Now, beta is bounded between 0 and 1, but you can, of course, apply it to between 0 and 100. Let's multiply by 100. You can bound it to, say, -5 to 72, to plus 72. Just shift it, right? Okay. And then you go to multivariate. Now, multivariate is a smaller world. You have a lot less number of multivariate. Now, let me tell you a story. Well, not a story. Traditionally, in life, you will go to the university and you will only know one multivariate distribution. Okay? Traditionally, that's life. That's life in the past century. You will know one multivariate distribution, and that's multivariate normal distribution. Okay? If, and I hope you are better than that, you learn how to, you become more inquisitive, you find out some more. There are more bigger other families, other types. But the more general way is called copular. If you think about it, remember I just turned that graph around during the break. I don't know if you saw, some of you. Okay. I showed this to some of you during the break. Hold on. I showed this to you. Where's the old faithful? Right. Okay. Remember this picture? This is multivariate distribution. Well, this is actually histograms from data. But let's say you build a model. You can see that there's X and there's Y, or X and X2. So this is multivariate because it has two dimensions. There's one dimension, there's another dimension, right? But if you ignore the second dimension, you look on the side, it looks like a one dimension. Okay, so this is a distribution of the duration time for the geyser to shoot. Now, if you want to look just the waiting time, you turn it on different axis. That's a waiting time, right? Mostly around 50 seconds, but a lot of time around 90 seconds, right? Now, normal, like I mentioned, you have a lot of univariate, but you only know one multivariate. Well, what if you have a way of putting a bunch of univariates together? Okay, multivariate normal means you start with univariate normal and univariate normal. Put them together, you get multivariate normal. But what if you want to use multivariate Poisson? Add one Poisson and another. What if you are even stranger? You want to add multivariate, but one dimension is Poisson, the other dimension is binomial. Is there a general way to put univariate together and construct multivariate distribution? Yes, that way is called copula. Okay, now copula is fairly advanced. You learn about it, and maybe you learn about some library, but you won't go very deep in it. But at least you learn about the principle. Okay, so you know that you're not limited to just multivariate normal. You can have multivariate anything. Okay, right. So let's look at what it would look like for you to do estimation problem. Now, there are a lot of trivial case. Let's go to this section. Okay. So I'm going to give an example, as a homework for you to go study a number of different distributions. I think that would save me time. I'll go straight to the parametric estimation part. Okay. So let's talk about parametric estimation. Now, I'm going to give you a more difficult problem. Example. Normally, you get a nice normal distribution, but I'm going to talk about more complex issues. So let's imagine we're trying to fit this geyser, which is bimodal. Okay, so it's going to be more difficult. So what I'll do, I'll just backtrack a little bit and talk about normal case, because not only is it easier to understand, it's also a lot more applicable. So you can go, you don't have to rely on my note now, you can go to Google. In this case, just go to normal distribution. Right. Well, the word normal distribution, okay, has another name. It's called Gaussian distribution. The reason it's called Gaussian distribution is because it was described or invented or discovered or written down by mathematician Gauss. Okay, Gauss is like he's like the biggest figure of his time. Okay, huge. He's like a super mega celebrity mathematician. Okay, so he discovered a whole bunch of things. Like I think if I want to add number 1 to 2000 in my head, okay, well, you can't do that, but obviously you can do this. You can add 1 to 2000, 2 to 1999, right? So you have 2001, and how many terms do you have? 1,000 of them. That seems like a clever solution you might think of, but Gauss came up with that when he was 4 years old. So very smart guy. Okay, anyway, so this is called Gaussian distribution. Why is it also called normal distribution? Why is it called normal distribution? Because it looks normal. You see this a lot. Okay, it looks normal. So that just begs the question, why does it look normal? Why does normal look like this? Okay, and this is where you get to maybe a side topic that doesn't proceed to estimation, but it's called central limit theorem. Okay, and central limit theorem is extremely important. Now, you saw from before the bathroom break, right? I can make Bernoulli, independent Bernoulli, right? Add them up, and what I have is binomial. Okay, the central limit theorem says If you didn't start with Bernoulli, in fact, you can start with anything, just about anything, right? And you take enough of them, like 30, 40 of them, and add them up. Maybe divide to make an average. Sum, average, same deal. Okay? You can take the sum or you can take the average. It doesn't matter what you start off with. Eventually, you end up with something that looks like normal. And that's pretty cool. And you already saw that in the previous thing. If I have enough, now I have a discrete distribution, right? But if I make n large enough, it starts to look like, what does it look like to you? Normal distribution, right? Now, this is not a surprise to you because when n is small, it already has the middle peak, right? The point is you can start with some really weird distribution. And let me go to the wiki page. You should have that. Central limit theorem. Yeah. Let's say you start with something really weird like this. Okay. By the way, what's a Bernoulli look like? It's just two column, right? One at 0 and one at 1, right? You can start with something like this, right? But if you don't take one at a time, you take 50 at a time, and you add them up, or you take an average. The distribution of that will converge to that nice shape. In the limit, that means as you have more fine-tuning, theorem means it's proved mathematically. Central means it converges to the true mean. So this thing, it has a weird shape, right? But it does have its mean, right? The mean is somewhere kind of there in the valley. The point is, if you take enough sums, take enough or big enough lot to sum, okay? Now in this case, you take the average. So you take the sum and divide by the number, say a sum of 100 at a time and divide by 100. The distribution of that would center around that original mean. But it would have the nice shape. This is an important thing. It's not just limit to central point. It also has that Gaussian shape. Okay, and this is proven mathematically. Now, I want you to be educated member of the society. And if you go to internet, you hear skeptics say things like, that is just a theory. Well, whenever someone says something like that, you can bet 50% that either he's using the word wrong or he's stupid. Because a theory is not a hypothesis. What he meant to say was, that's just a hypothesis. Okay? So there's a degree of truth. You hypothesize that the data has this distribution. That's your hypothesis. Once you prove with enough data, you publish your paper, nobody disputes it. 50 years later, they'll still find the same distribution that you did. Nobody believes in anything. The body of evidence is insurmountable. It's unbelievably obvious. It becomes a theory. A theory is basically empirically, scientifically well-proven hypothesis. Now, because it's science, there's always a possibility that 100 years down the line, you'll be surprised, but right now you won't. The difference between theory and a theorem is that a theorem does not rely on empirical proof. It relies on the logic of mathematics. So once a theorem is proved, you don't have to wait for a surprise in another 100 years. A theorem is a theorem. It stands forever. Okay? So if you're a mathematician and you came up with a theorem, you already are immortal. Okay? That lives way beyond your life. Well, central limit theorem is a theorem. So you can be pretty comfortable using it. Okay. Right. So having said that, so that accounts for why you see a lot of normality. Okay, see a lot of normality in real life. Okay, because a lot of, you can think of big event as summation of small events. And this is an analogy. This is probably not right, but if you think about it, if a stock return is normal, you can imagine that the return movement is a sum of little movement, and little movement can be increased or decreased, but a whole bunch of them, you add them together, and then you get this normal curve. Yeah, that's an analogy, by the way. It's not a proof. Okay, so let's look at the example that I brought to you guys. Now, I cheated a little bit. Well, because remember I told you that if you are a good statistician, you come up with a bag of mathematical functions, and then you sort of like, nah, that looks like a Poisson. Okay? Well, there are two ways of making this judgment. First is what we've been talking about, visualization. That looks like a Poisson, so let's put Poisson to it. But there's a more fundamental way, because you know the random process of generating that. Remember, random variable comes from random experiment. And then you take the outcome, but you map the outcome in numerical form, in numbers. You assign number to outcome. So the value it takes on becomes a value. So that's why you get random variable. Okay, so it's a randomness. But just now, you can imagine that you have in your bag, in your purse, binomial distribution. You look at the data, and it looks like a binomial distribution. That's one process. The other process is somebody told you that this came from independent Bernoulli events. You knew it's going to be binomial from the construction. A lot of data science works like that as well. I know this is going to be a Poisson distribution. Why? Because you are counting the number of independent events that happens in real time. For example, if I'm going to say the number of sales or the number of arrival of a client at a storefront, and all I have is basic assumption like no two clients arrive at the same time, no simultaneous events. So one client arrive at a time, and the length of time that you wait for the next client is independent. In other words, if you waited 10 minutes from the last client to the previous client, you still don't know how long you're going to wait for the next one. So it's totally independent. Independent inter-arrival time, okay, and no possibility of double arrival. Things like this gives you say, if this is the random process, okay, the stochastic process, I'll talk about the word stochastic later, random process that generate this, chances are, if I count the number of customers over a period of time, it's going to have a Poisson distribution. Not only that, if I want to model the inter-arrival time between customers, it's going to be exponential. Okay? So this is an example of a knowledge base, except this knowledge base is from mathematics rather than business. You have this process of arrival of event, independent arrival, one at a time. This whole process is called Poisson process. And the number of arrival over an interval of time has a Poisson distribution. It's a Poisson random variable. And the inter-arrival time is an exponential random variable. It's a random variable with exponential distribution. Okay? So if X is a random variable, it is a random variable with a distribution. That's how I can say interchangeably. Now, let's look at this. In the recipe that you saw in Wikipedia, very rarely will you have multimodal distribution. Beta is one of them, but okay, normal isn't. So this doesn't look like you're going to have a nice easy fit. Okay, nice easy fit. Now, so I'm going to cheat a little bit. I say, I have no idea. I ask the computer, okay, to try as many as it can, subject to some limit. There's some, meta parameter as to what to search and what not to search, I think. So this is the data. I take the old faithful data, take all the data, and take the first column. If I take the first column, what I'm talking about, just the eruption time, right? In seconds. So I'm just taking one dimension. I'm making a univariate example. So let's make histogram. Yeah. So this is basically what we saw earlier when I stood the histogram on the side, right? You guys can see this. Yeah. So around 2 minutes. It's a lot of peaks. Around 4 or 5 minutes. Okay. So this is the bulk of the long-lasting eruption between 4 and 5 minutes. But there's some that, just last 1 minute, half a minute or something. Okay. So what I did, I said, if this is the data, I find distribution equal to, please Mathematica find a distribution for me for this data. That's what I did. I literally just did that. Find distribution, and the outcome gives you this. Now, how do you read that? It says it's mixture distribution. That's a word you haven't heard. And it's a log normal distribution. You also haven't heard that. And you also say normal distribution. Well, normal distribution is this. Okay? A log normal distribution just works like a normal distribution, except it works only on the positive. So the log of x is normal. If log of x is normal, x is log normal. So it looks like a mixture of this shape and this shape. Let me say that again. This normal distribution gives you one shape, right? Symmetric. This log normal gives you another shape. But if you take 60% of this and 35%, 64%, 64.2% of this, 35.7, 35.8% of this, see this adds to 1, right? And you put them together, you get that distribution. So this is Mathematica's way of finding for you. Now this is state of the art, like Mathematica can do this for you. But let's just go back 100 years before you had Mathematica. What you would have to do is look at this piece, okay, and look at your bag of probability models. I don't have continuous bimodal distribution that is not symmetric. So what I'm going to do is I'm going to say, how about it's a superposition of two distribution mixture, right? It has two bimodal, so maybe the two different population. So there's some eruption from the smaller pocket of rock and steam, and there's maybe a bigger rock and bigger steam, and they kind of come together maybe, so there are two different processes. So I'm going to say it's a mixture of two things. And one thing has a normality shape, like sort of like symmetric shape. The other one has log normal shape. Now, if I'm really good, then I have the parameters. How many parameters do I have? Normal distribution, I'll go over in detail, has two parameters, mu and sigma. Log normal also has this mu sigma, so that's 4 parameters. And you have another parameter that tells you how many proportion of one versus the other, the 35% versus 65%. So you have 5 parameters. Those are free parameters. I can tweak them one at a time. I can tweak them all at the same time. I can tweak whatever. My process is to come up with the 5 numbers that best describes this. And the number that I would have had to come up with on a piece of paper would have been 4.3, 0.42, 0.7, and 0.12, and 0.35. This one I don't have because that's just 1 minus this. Right? This is what is called parametric estimation. So in Mathematica, you can also do it old-fashioned way, which is to come up with the distribution first. In this case, I cheated because I kind of like assume that, you know, I can make anything. I can say log normal and log normal. Oops, I think I did some error here. But anyway, it should come up with some parameter. So that would be the process. The process is you whip out distribution model. In this case, I'm at a loss. I can't really find anyone that has this shape. Okay, the closest I can find is beta, but beta is no good because beta is bounded, and it's not symmetric, but it's bounded. So I say, well, let's just say, nah, let's throw in two things, normal and log normal, and have some combination thereof, and find the parameter. Now, the concept of doing that technically is called maximum likelihood estimator. Okay, where's the word? I think I'll show you the word. Oops. Again, I'm writing the textbook as we go along, so I may not have all the text. Basically, it's called maximum likelihood estimator. It's saying that what is the value of the parameter that made it most likely to see the data that you just saw. Okay, ma? Right? You start with you can visualize the data and come up with a hypothesis that it is binomial, or you knew that it's generated by independent coin toss-like events. So you say, okay, I'm convinced it's going to be binomial. I'm convinced it's going to be binomial. Okay? Once you're convinced it's binomial, let's say you also have an idea that it's going to be n is equal to 10. Okay? Because it can't be bigger than that. So the only thing left is P. The maximum likelihood principle means the P that you should use is the one that generates the binomial distribution that best fits the histogram. It's maximum likelihood because it means that that P makes it most likely to see the histogram that you just saw. And of course, mathematically, when you do something like this, what does that come down to? Maximizing the likelihood. When you maximize something, what do? You go to calculus, right? Now, let me show you in principle how this is done. You don't have to do it because most of the time it's done for you. วาดรูปนะ มันไม่พอ okay, clear. Okay, right. So let's say you have this distribution and you have this distribution. Okay, which one is more likely? Well, it's the one that best fits the histogram, right? How do you find that? For each point in the histogram, say each point in the histogram, this point, right? This point. Under this model, it has its value. Okay, has its value. Think of it as probability, even though it's probability density. Under this model, it only has this value, right? So which one is more likely from the standpoint of this value alone? It's this guy, right? Let me just draw a nicer picture. Okay. Now this is your histogram. Okay, let's just make a funny one. It looks like this. And these are your candidates. Okay. Okay. From the point of view of this data point, which one is more likely? this one only had this value, this one sets that value, right? So if all the point has its own value, basically it's the value of the PDF, right? But when it's applied to an individual point, I call it likelihood of xi. Now, if the likelihood are together, just one point, that's no good, right? I want to do all the points. So I multiply by the likelihood of x2 and likelihood of xn for all the sample, right? Then I maximize that. Now, this is where it gets tricky. Multiplication n times is never fun. But you know something from high school, that logarithmic function is strictly monotonic. Okay? And you know that it applies to positive quantity. And you know that likelihood is positive quantity. So instead of maximizing this, you take the log of this first. What happens when you take the log of the product? Guys, you must have gone through high school, otherwise you shouldn't be here. If you don't know this, I'll get you kicked out. Come on, you don't want to throw away your education because you can't tell me what the log of the product. Logarithm of the product is, it's the sum of the logarithm, right? So you convert multiplication into addition. Come on, guys. Log of product equals to come on, you must have seen the whole page like this.
Yeah.
Who hasn't seen this? Report yourself to the registrar. Okay. Multiplying n numbers together is no fun. Okay. But taking a log is not so bad, and if you do it n times, you can add them. So it's usually called maximum log likelihood or maximum likelihood. Now, the P that you get from that is therefore called maximum likelihood estimator. Okay? So, in theory, that's how it's done. And you come up with a formula because they did it for you, and then you just plug in the number and blah, blah, blah. I should make it a programming exercise, you know, maybe something like create a Python program that finds the lambda of an exponential distribution that fits the data, something like that. Okay, that's a good exercise. That's a good. Okay. Right. So now, in reality, a lot of life, a lot of your time will be spent on normal distribution. So I would assign maybe as a reading. Now, this I haven't gone to the remainder of statistical inference yet. Okay, but basically it looks a bit like this. I just tell you the pipeline. เอารูปเมื่อกี้ใหม่ดิเอาว่างๆใหม่ดิ here. Okay, so just now, right? You say, I have this data, and I have this, and I throw it on top of it, and I tune the parameter so that it looks like that. By the way, the normal distribution looks like this, right? It's centered at mu, and the width is given by this, and that covers about 68%. Okay, so you know that. Well, how about this? How about I claim, okay, that something is not toxic, let's say, okay? Let's say that there's a distribution of contaminant in drinking water that's acceptable, okay? So let's just say that if x is greater than 7.5, bad. Okay? If x is greater than 0.5, it's bad. What I'm going to do is to say x is normal mu sigma square. Okay, under assumption is normal. The null hypothesis, H stands for hypothesis. Null hypothesis doesn't mean it's something you want or something you like. It means it's the most specific statement. Okay? The most specific statement you can say is that mu equal to 7.5. Okay? Alternative is mu is greater than 7.5. Now this is called one-tail hypothesis because it can fail on one side. You can also say something like hypothesis is not equal to 7.5. So two-tail. All right. Basically, the way, no, Google, don't use this. This is very bad handwriting. Hypothesis testing. I have to teach statistics to Satsin students, so I think I'll do the I'll capture some of the highlight textbook and I'll give it to you guys. Okay, but here's the deal. This is what you do. Under null hypothesis, you get this. Okay, forget sigma. Sigma is the width. Let's say you knew the sigma. Okay, and you fit the mu. But anyway, under null hypothesis, this is 7.5. Null hypothesis. This is null hypothesis. Okay, and how ugly would the sample have to be for you to not believe this? That's the whole game. Okay, watch this. If this is 7.5%, sorry, this is the value is 7.5, and the average you came up with, is here. Are you okay? I'm okay with that. How about here? That's a bit uneasy. How about here? How about here? Definitely no. So what you do is, under null hypothesis, you say, well, let's give benefit of a doubt of only 5%. This is opposite of the benefit of a doubt. It's saying that under this case, there is 5% that yes, the contaminant on average, the claim is on average, the claim is not on individual. On average, contaminant is no higher than 7.5, whatever unit of that is, okay? But because of sheer luck, sheer sampling luck, I get number that is this big. So I'm going to put a fine on that manufacturer. So this means that I'm giving a fine to the manufacturer, even though he's not guilty, right? But certainly you have to have some kind of cutoff. You look so guilty. So I'm allowing 5% of type 1 error. It's the probability that no, hypothesis is right. Null hypothesis is right. But the evidence is so ugly against you. Too bad. Sorry, guys. Okay? Now, how big or how small is that number? Well, if this is, say, a pharmaceutical example, right? And this is about imposing a fine. 5% you might say is even generous. Maybe because this is a health risk, right? I'll cut it down as 10%. Right? Because, you know, what's the worst that can happen? Just get fined and then you revise the process. So it's a very big thing. On the other hand, if the penalty is death, right? You certainly don't want the big one. You want like very tiny margin of error. So how the threshold of cutoff depends on your preference, on your priority. What they would report is what's called a P number. If the data is here, say something like here, the P number is the probability to the right. And then you decide whether or not that's too big or too small. In other words, if the P number is 3%, you say that even if you're not guilty, there's a 3% probability that you will show the number this bad or worse. Okay? And then you tell yourself, well, this is a safety public health issue, so 3%, that's not acceptable because my threshold is 10. But if it's a death penalty, I'll say, well, I'll give this guy benefit of doubt. I'll just set the margin of type 1 error at 0.1%. 3% now I'll let you go because I don't want to execute you. Okay? So this is the rigorous way of doing statistics. You notice that it builds up from the intuitive understanding of how your data is distributed. Again, from two sources. One, from looking at it. You know, when I say looking at it, you actually have diagnostic, like measuring the mean and so forth. Then you know if the random process is generating is follow a certain pattern, certain phenomena. You can say, oh, it's Poisson, it's blah blah blah. And the diagnostic would be like medical thing, you know. You take a blood test, this indicates this and that. The symmetry, the skewness is 0. So you know that it's not log normal, for example. Okay? Something like that. So you have some kind of, it's not just looking with your eyeball, but it's looking through first moment, the means, the mode. Second moment, the standard deviation, the skewness, the kurtosis. If the kurtosis comes up to be 7, then you know it's not normal. Okay. In fact, there's a normality test based on the name Jacques Barra, 2 guys. Basically, he's saying that if it's normal, it has to have 0 skewness and kurtosis of 3. Anything different than this, then chances are it's not normal. Okay. So it's like hypothesis testing, but on the distribution itself. So it's a lot more intricacy. The basis of this hypothesis testing will form everything you do in data science. Not exact step, but this sort of thing. Okay. And so with that, I think it's a good time to think about what we're gonna do with the course. Now, let me do a little housekeeping. You guys have found the group. Anybody homeless at the moment? No. Okay. Any house is not full. Everybody has full house. You need one more. That's okay. One person doesn't mean anything. You can go with this what you got. Okay. So, how many teams we got? You guys have to register. Now, homework. Sorry, homework. I'll tell my TA to change the submission to allow for attachment. But if you're going to attach, you better attach something good. If you're just going to attach a doc file, I'm going to subtract points. Because, you know, just put if you can write in the space, write in the space. But if you have graphic presentation, you have diagrams, you have this and that, and you have a full report, yeah, by all means. Okay? Also, don't use Google link. Okay. If you have something really fancy to show, definitely submit as attachment. But if it's just a text answer, just write in there. Okay. And I'm not going for length. I'm going for insight. I told you before the class that it's a lot harder to write 1-page report than it is to write 3. Okay. So if I didn't give you enough time, then I would accept a 5-page report. But I gave you 2 weeks, so I would expect a 1-page report, maybe 2. Okay. But at this point, just check your grammar and make sure you write properly. And if it's a little bit long, that's okay. Remember, it's 2 different perspectives here. It's a one-to-many, and you'll find yourself in a lot of situations like that. Whatever you do, you invested in the effort. There's always a tendency to show too much of what you did. Think of me as completely uninterested, and your boss will be like that. Your client will be like that. Everybody you interact will be like that, because it's everything to you, but it's only one of many to them. Okay, so make your presentation to the point, get my attention, like you're trying to sell something. Okay, in this case, sell the insight. So, I'll work out the assignment maybe a little bit more, but now I call it attach that. Okay, good. So do attach if you have something good, like you develop another demonstrator or something like that. Project-wise, again, I would encourage you to literally get the software installed. It's much easier and much nicer to work with that than with Python. But if you're confident or you're cheap, go with Python. But it takes a lot, and I can't help you. He can. Okay, so let's do that. Okay, Kap. You guys are looking good. Let me go through the first week and see if we are communicating on the same page and see how that goes. Okay, Kap. Have fun. Okay, see you next Monday. Sawasdee krap.